Here I've depicted a container full of water. You can see the little waves up the top. You can see the shark's fin sticking out to indicate that this is water. Of course, maybe it's not water. Maybe it's some other liquid that's compatible with the shark. Okay, anyhow, we have a point A at the surface of the water. We have a point B at some depth within the water, and we have a delta y AB being the displacement from the level of A down to the level of B. Now we want to figure out the pressure in terms of all these quantities. So we imagine a tube, or I've drawn, instead of a round tube, I've drawn kind of a square vertical prism. But this indicates how much water we have between here and here. Just a section of the water, and I've enlarged that over here. The prism has dimension delta y AB, actually the magnitude of delta y AB, and a cross-sectional area ACS. Now we know from what we've seen already then that the volume of this tube is the cross-sectional area times the altitude. The weight is going to be density times volume times the acceleration of gravity. Density times volume gives you the mass. Multiplied by the acceleration of gravity, you get the weight, and that gives you the expression rho g A cross-sectional times the absolute value of delta y AB. And the delta y AB, of course, is the depth of this point B relative to the surface. Now, the magnitude of the change in pressure between point A and point B is what? It's going to be the weight over the cross-sectional area, because the weight is the force. Cross-sectional area, force is distributed over the cross-sectional area. That's your definition of pressure. And we see that if we put this expression for the weight in, the cross-sectional area is going to divide out. We're going to get rho g times the magnitude of delta y AB, so that the pressure change is going to be equal in magnitude to rho g delta y AB times the magnitude. But it's in fact going to be equal to negative rho g times delta y AB. And we can invoke common sense. There are other more formal arguments we could make, but obviously the pressure increases as the delta y AB is negative. The pressure change from here to here is positive. Pressure gets greater, so that's going to be opposite to the direction of change of the delta y AB. One reason for the negative sign here. Now, from this relationship, we can easily subtract or add rho g delta y AB to both sides, and we get delta P from A to B, change in pressure from A to B, plus rho g delta y AB is going to be 0. Change in the pressure, the change in rho g y is going to add up to 0 for these 2 points. Now, I want to think about what happens if a little chunk of water is expelled from this container. Okay, here's a little chunk of water. We've already analyzed this for 1 centimeter cubed. We found the velocity. How did we do that? We analyzed what the pressure at this depth does to that cube. The pressure acts on, if this is a cube or rectangular solid, whatever it is, the pressure acts on this end as well as on the sides, but it doesn't act on this end. This end is open to the atmosphere, where the pressure is presumably the same as it was up here. So how are we going to analyze that? You might want to think that through for a minute.